Okay, going live. Okay, got it. So I think we're good to go. So first we'll start with a bit of introduction. So hello everyone, my name is Yan Sheng, and together with me we have Sanklan, and two of us are the co-presidents of the Trinity College Science Society. This is our first talk in this academic term, and it is our honor to have Professor Stephen Leone with us today. As a quick introduction, Professor Stephen Leone is the John R. Thomas Indoe Chair in Physical Chemistry, Professor of Chemistry and Physics at the University of California, Berkeley, and he's also a faculty investigator at the Lawrence Berkeley National Laboratory. His research interests are ultrafast and attosecond laser investigations of atomic, molecular, and solid-state dynamics. And today, Professor Leone will be speaking about ultrafast dynamics with Xray Eyes. And before we start with the event, there are just a few logistic points which Sanklan would mention.
First of all, the audience are muted by default to prevent unnecessary background noise. To request an unmute, just click the raise your hand button and we'll help to unmute you. Also, the video stream is off by default, but you are encouraged to turn your video on for a more interactive experience. And you're very much encouraged to ask questions during our Q&A session, which will be after the main presentation. And just again, to request an unmute, click raise your hand, or you could use the chat as well to ask your questions. Finally, as mentioned in the email, the event is being streamed on YouTube. And I think that's all from us. So let's welcome Professor Leone to take the stage. Thank you very much for being here.
Okay, thank you very much. This was a super well organized event, and I really enjoyed interacting with the organizers and putting this together. What I'd like to talk to you about today is recent work in our lab where we do spectroscopic investigations in time with X-ray photons. And I'm going to give two examples. One is molecular and one is solid state that have come recently from our lab. And this picture is like a typical setup. You have a high-powered laser, and then you convert this laser into X-rays by a method I'll talk about. And then after that, the whole setup has to be in vacuum chambers because the X-rays would be absorbed in very, very short path lengths. And so we like to call this extreme ultraviolet or X-ray probing. And the simplest possible way to do this is by methods called transient absorption, which I'll explain. And it invariably makes us get into studying what we call core level transitions. So I also need to explain that. And it allows us to get at electron dynamics. That's going to be the really big thing that we understand from this work. So if we think about time dynamics, you know, this goes back more than a century that people had put trip wires. Edward Murbridge had put trip wires on a racetrack, and when the horse would gallop, it would trip cameras, and you would get these photographs of the horse galloping. And what was a big revelation is that in one or two of the frames, all the feet of the horse are off the ground at one time at a gallop. So this was probably our first example of like time resolved dynamics in a sense, you know, which physicists and chemists love to apply now in femtosecond and very, very short time scales. This led Walt Disney to start to realize that you could fool the human eye with enough frames per second. So you could draw cartoons, and if you had enough frames per second, it would look like it was a continuous movie, basically, of the event. So in the real world now, you know, we think about clocks and time, and you know, at the National Institute of Standards and Technology, they try to make very, very accurate clocks, and they're used in global positioning and things like this. And time is a parameter that the experimentalist sets. It's not a quantum mechanical observable. There's no operator for example, in quantum mechanics for time. And what a lot of people might not realize is that in molecules and atoms, there's also like a whole lot of little clocks happening, the periods of frequencies of vibration or rotation or electronic transitions. And so these are keeping time for us in a lot of different ways. Now, to get the very shortest possible times, we needed some powerful lasers that could produce very short pulses. And what was realized in quite a long time ago is that these very short pulses would easily damage the amplifiers that you need to make the high energies so you can do experiments. And so what was realized at the time by Donna Strickland and Gerard Moreau is that if you stretch the pulse out in time first, and then do the amplification, and then recompress the pulse again, you could then make these very high power, high energy lasers. And so today we go out and we purchase a short pulse laser that has high energies that we can use for experiments, but maybe not so easy to realize that, okay, a long time ago, people had to invent that technology to get these short pulses without damage to all the optics. And this was a recipient of the Nobel Prize in Physics in 2018. So now we have the type of lasers that we need, but we not always have the time that we need. And what this shows is the pulse duration of lasers on a logarithmic scale and the year in which they were invented in the laboratory. And what you see is that for quite a long time ago, we had picosecond, nanosecond, picosecond lasers, and then there was a very long plateau of femtosecond lasers, and this is the period where the Nobel Prize was awarded for femtochemistry to Ahmed Zewail. But then you see here at the late 90s, there was this abrupt decrease in pulse duration. So these are the durations of pulses, basically. And what happened here is the invention or the utilization of high harmonic generation processes that allowed one to make much, much shorter pulses by moving into the X-ray or the extreme ultraviolet. And now there's a claimed world record of a pulse as short as 43 attoseconds in duration. But it's useful to map this on the time scales of molecules and atoms and solids and things like this. And so you see, for example, this greenish region is very similar to the time scales of like vibration, where we just have two atoms attached by a spring and they're just oscillating in and out like a harmonic oscillator. But if we want to actually observe electronic time scales, we need to get down into this kind of bluish region here. And if we were to pluck an atom out of a molecule, pluck an electron out of a molecule and ask how fast would another electron refill that orbital, we're talking about these very short time scales here, and hence the electronic dynamic time scale. Now, how do we make these harmonics? So it's almost seeming like magic. We focus a very intense laser into, say, a rare gas like neon or helium, and kind of by magic comes out from this intense pulse the odd harmonics of the output. And if you make this number n very large, you can get very short wavelengths of light, very high energy photons. So how does that process work? And it was explained in these two papers in a semi-classical way in the early 90s. What the strong field will do is bend over the Coulomb potential of an atom and allow one of the electrons to begin to tunnel out like this. And when it comes out from the atom, it gains a lot of energy from the laser field. But then the laser field reverses cycle. So if you look down here in the corner, you see the laser field is oscillating like a sine wave and at some point it will reverse its cycle and drive that electron back on the atom. And a small fraction of the time, that all that energy that's been acquired by the electron can be emitted as one of these high harmonic photons. Now, if we make the pulses short enough, like shown here, this is what we would call a few cycle pulse, then we can arrange it so that we get only one burst of the high harmonic radiation and therefore make isolated attosecond pulses. If we have longer pulses, then we get pulse trains of attosecond pulses. So what's cool about this method is that we not only make extreme ultraviolet and X-ray photons, but we also can make extremely short pulses by these means. So let's put in perspective where these photons are. And so this is just the electromagnetic spectrum along here, you know, from radio, very long wavelength to very short, like X-rays and gamma rays and so on. And these are some of the spectroscopic tools that we know about, like magnetic resonance, or we can do vibration rotation spectra or visible electronic spectra. Where we're talking about is up here in this region of X-rays that we call inner shell transitions that we're manipulating. And I need to show you on some diagrams what kind of information we get from inner shell transition. Now, the human eye sees just this small, narrow region here, but we have excellent detectors to cover all these different regions whenever we need it. And so we can have, for example, an X-ray camera to look at the spectrum of an X-ray, and that's what we're going to be talking about today. I need to show you. Anything or okay?
I think there might be a small echo, but I think it should be good.
Okay. So now, when did X-rays come about? It turns out in, you know, also more than a century ago. And Wilhelm Röntgen, you know, saw the X-ray of his wife's hand here, and she exclaimed that she had seen her death, basically. And this was a better image. It's quite remarkable, actually, because it, you know, even in those earliest days, how good you could get an image of like the bone density in someone's hand, basically, and even the ring on the finger and everything. So you can peer through materials with X-rays, and I think that's the really important thing to understand. But these images, they're not spectroscopy. These are images of like changes in density and so on. Now, if we think about, you know, spectroscopy a little bit, like hummingbirds can actually see in the ultraviolet, like bees and hummingbirds and so on. And so our human eye is limited to this narrow range of visible, but hummingbirds and so on, they can start to see out in the ultraviolet. And so, you know, it might not be crazy to wonder, well, what could you see if you were in the X-ray? And of course, in the science fiction world of sort of radiation and X-rays, there were a lot of movies and comics and different things that had, you know, explored this. And this movie called The Man with Xray Eyes with Ray Milland actually follows a lot of the observations of Röntgen in his first discovery of X-rays. And the concept in this movie was that there were some chemical drops you could put in your eye to observe X-rays. And he was a physician, and so he could actually look at people and say, well, you have a tumor, or you have this problem, or something. And so, you know, we also know from comics that like Superman was always, you know, looking through walls, or could, you know, melt like icebergs and things like this, you know, in like the first reference to X-ray eyes in the Superman. But, you know, it's actually interesting to ask, well, who was the first to supposedly have X-ray vision? And it turns out it was Olga Mesmer in a comic book superhero in like 1937 and 38 in a pulp fiction magazine called Spicy Mystery Stories, The Girl with the Xray Eyes. And so this Olga had this dormant superpower that only became noticed later in life in this comic. So now if we apply X-rays in the modern world, we see tremendous benefits to X-rays. For example, you can have computer tomographic imaging. These are scans of slices of, say, someone's brain. You can look for tumors or, inappropriate, items in your brain and so on. Or you could do diffraction of molecules, like large biological molecules, proteins, and, form crystals. And we get all these diffraction spots. And if we do the transform of this data, we can get precise distances between the atoms. But none of these are actually spectroscopic. And so I want to move now into the spectroscopic realm and show you by way of this example. So these are 4 iron complexes and data that I just took from a literature article. And what you see is that the iron in all these 4 different complexes at about 700 electron volts in the X-ray has all different spectroscopic features. So there's like a fingerprint of spectroscopic features that one could recognize very clearly that these compounds are all different. And if we could harness that potential and apply it, if we could understand why the features are doing what they do and how to apply it in a time dynamic sense, then we could do some really truly new kinds of experiments. So this is the area that I want to talk about, is X-ray spectroscopy, and that's done a lot at synchrotrons and so on in static realm. So just one little energy diagram to give you an idea of this. Suppose we had a molecule like AB, and we had the inner shell electrons of A and the inner shell electrons of B here on the left and the right sides respectively. And then we had, let's say, valence shells of the orbitals of the molecule itself. And say there's a vacancy here, or let's say this electron was down here initially and then we promoted it. And you see from the perspective of either the A or the B atom, we could make X-ray transitions to wherever there would be an orbital vacancy. So if we promoted this electron here by a transition with, say, visible light, we could then observe the new vacancy here, or the blockage of the absorption by the placement of this electron in this orbital. So it's this power to look through different atoms, to look through the eyes of different atoms, that's very special in X-rays. And it's state selective and element specific. So if this was like iron and this was oxygen, they would have very different transitions. And it will be sensitive to the oxidation and charge states and even spin and chiral sensitive. So it's a very powerful kind of spectroscopic tool that has not been used very much in measurements, in time dynamic measurements. So we construct in those big vacuum chambers a setup with like a lot of optics. Some of them are X-ray optics, like toroidal mirrors and variable line space gratings, and some are external optics or visible optics, where we pass beams through a small hole and then merge it with another beam and so on. And in the canonical type of setup, what you need is 2 beams, one of which passes through a delay line, so you can set the timing of the delay by the speed of light on the table. So by just the distance that the pulses travel, we can alter the time delay and then merge them in an experiment. So here, for example, we could have an experiment in a gas or in a solid. We put a solid in, we have a pump, we excite the solid, then we come through with the X-ray and then we probe. And these short pulses are remarkable because they have extremely broad bandwidth if they're very short, like isolated attosecond pulses. So for example, a 100 attosecond pulse is almost 20 electron volts wide. So you have a way to pass a pulse like this through a sample and then spectrally resolve it with a grating by dispersing, and then see that result on a camera. And these are just two examples of like how short are we doing. Like with our visible optical pulses, we get down to about 3.5 femtosecond. And with the X-ray or X-UV pulses, we get down to about 170 attosecond in many of the experiments. So let's just have a view of that. So here's a spectrum of high harmonics that we can make in the lab. And you see this extends from 180 EV to about 360 EV. And what's really curious here is that there's a big notch in the spectrum of these high harmonics. And this is the carbon that's just deposited on the mirrors. It's just absorbing a little bit. And so right away you realize, well, we'll be able to study carbon and all different forms of carbon and molecules and things, and look at different spectroscopic features of carbon, because it's very strongly absorbing just from the few deposits that are on mirrors and so on. And here are the individual harmonics that show up in this particular spectrum. So they're separated by about 3 electron volts for a titanium sapphire, or in this case, infrared pump laser. So they're separated by maybe 2 to 3 electron volts showing up here in the spectrum. So now let's think about a scientific problem like that you could apply this to and why it would be useful. So in chemistry, for example, surface crossings are very prevalent. We have 2 electronic states of the same symmetry, and they can do what they call avoid the crossing, basically. And so we have 2 separate states. But when we're launching a system on, say, this S1, the singlet S1 state, it has a finite probability to jump and to come out on the singlet S0 state. So these crossings are kind of ubiquitous in chemistry. They're responsible for the healing of DNA. They're responsible for vision, the photoreceptors in vision. They're pretty much prominent everywhere, and they involve a change of electronic state. So we call these avoided crossings, or if it's multidimensional, we call them conical intersections, and they're ubiquitous in chemistry. So the thing is, the electronic character changes when it makes this crossing. And so the X-rays are just the perfect kind of system to be able to see that change in electronic character. And one kind of character that is very obvious is if you made a crossing from a singlet state to, say, a triplet state. If this, instead of this being the ground singlet, if this were the first excited triplet state, that gives a remarkable change in electronic character. The singlets are spin paired and the triplets are spin unpaired, and so it changes the electronic character. So in a molecule like acetyl-acetone, this molecule has 2 carbonyl-like groups and a carbon structure like this, 5 carbons, 2 oxygens, and it loves to fold up into this ring-like form where this hydrogen atom is shared by these 2 oxygens. So about 93% will end up in this ring-shaped form. We call it the enol form. And there's a lot known about the photochemistry and the longer, time scales of what can happen. But one thing that had been missing in all of these investigations is to find the triplet state in this type of molecule. So when you excite, like with ultraviolet light to the singlet manifold, it had been very elusive. No one could ever find where was the triplet and when was it formed, basically. So I'd like to show some evidence for this. So the first thing we need to do is just have a spectrum of the ground state of this molecule. And so, for example, if I label these carbons 1, 2, 3, 4, 5, and they're color coded, I see, for example, that this Xray spectrum, which is the black points here, is actually composed of some very discrete peaks. Like this red peak is this number 3 atom here. And these green and blue are the 2 atoms on the carbonyl groups. So right away, you realize that you're doing an atom by atom identification of where in the spectrum you're seeing different features. And it turns out this number 3 atom is very sensitive to whether or not the spins are paired or unpaired. So when the molecule would change from the singlet to a triplet manifold, you would see it very easily through this number 3 atom. And we know that from theory. So we're looking always at the carbon spectrum here. And I just want you to look here for a moment. So this is a simulation from the theory of the triplet, the first excited triplet state. And it's shown in a differential spectrum. So it was shown in the way the data would come out of the recorder, that we would have a pump on, pump off, and then subtract the 2 spectra and see what's left. And this peak here comes from that number 3 atom. And you see it here in the experiment, like very clearly. And the question is, well, when do you see it? Well, it turns out it appears in about 1 to 2 picoseconds. So this spectrum was taken at like 7 to 10 picoseconds, but we get all the kinetics. We can actually determine the exact lifetime of the rise, the time scale of the rise of the triplet state. So just like we can do for the triplet, we can also simulate spectra for, say, the second excited singlet state and the first excited singlet state and so on. And we can show that this feature is unique among all these spectra and therefore evidence of the triplet. So this is the first time that the triplet was found. And I use this example because it's so clear in terms of like which atom was responsible for showing the triplet character. Now I'd like to just consider one more example briefly, and that's the breaking, the simple breaking of a bond, the breaking of the CI bond, the carbon iodine bond in this isopropyl iodide. It's a gas phase molecule also. And you can think of this process in the following way. We excite the molecule up mostly to the triplet Q0 state, but then it undergoes a conical intersection and it can decide on 2 pathways whether to go to remain on that triplet or to transfer over to the singlet state like this. And these 2 pathways, they lead to 2 different excited states of iodine, the doublet P1/2 and doublet P3/2 iodine states. And this studying the final states has always been something that people have done a lot of work on, but following it through this crossing has been very difficult because there was no simple spectroscopic method to determine when did it make the change. And so this map of data here is looking through the eyes of the iodine, and it's from about 45 electron volts to 48 electron volts. It's the 4D inner shell transition of the iodine to the valence states, these valence states of the molecule as it breaks apart. And this is time going up along here. And now I want to reveal some arrows to show you. So this is kind of like the movie of what happens. So we start almost exclusively here on these blue arrows. And then it encounters the crossing and branches. A piece goes over here and another piece goes over here. And this short-lived state is it's already moved over to the red curve here, but it's still in the molecule. And then that short-lived state eventually goes out to atoms, and that would be when it goes out here to this asymptote. So remember, it's these asymptotic features that have been observed a lot, but we're trying to observe the change. And here you see it going along here and switching over to there, and we get the exact time scale for that, and then eventually tracking out on the different atomic lines, such as this. So these are two molecular examples, and I hope it is convincing you that we're making some of our own movies. Okay, they're frame by frame in time, just like Edward Murbridge did with the galloping horse, and we can follow like ring openings and charge transfer, many kinds of new processes. In future work in our lab, we hope to find diradical signals of signatures of diradicals and so on, and that you're cranking a little movie of what is happening in time through the electronic spectra in the X-ray. So now I'd just like to take one different example now, because I know many people might be materials scientists or thinking about going in that direction. And so what if we look at a solid? So what's different about solids is that instead of having discrete energy levels, we have bands now. And this is just shown for germanium here. Like we have a conduction band in germanium, and we have a valence band, and we have a band gap, like a forbidden region where there are no states. And we can excite across the band gap of this system. And then we can probe through the eyes of the atoms in the solid, for example, the germanium 3D inner shell. And we can see, for example, if we promote electrons from the valence band here to the conduction band, there'll be a reduction in absorption to the conduction band by the 3D shell, but there'll be new openings. There'll be a vacancy in the valence band, and what we'll see is disappearance, a decrease in absorption in the valence band as we create holes or the absence of electrons in this in the valence band. Let me just see. There's someone asking to admit. Yeah. Okay. So how about metal dichalcogenides? These are, 2D materials that come in layers, and they're bound by very weak forces. We call them van der Waals forces. So this is molybdenum sulfide, molybdenum, sulfur, sulfur, and then we can peel these layers off, and you can make single layers of materials. And what's dramatic and has been discovered about these materials is that when they're in the bulk solid, a lot of times they have what we call an indirect band gap, where we need energy from the lattice to make the excitation. But when we peel off single layers, they often become direct band gap, so we can require no energy from the lattice and just directly excite from the valence band to the conduction band. So let's just dream, what could we see if we tried to study such a material like this? And it's not going to be molybdenum sulfide, it's going to be molybdenum telluride. And so this is a map from about 30 electron volt to 45 electron volt of the molybdenum and the tellurium inner shell transitions and versus time. And the only thing we're doing is exciting across the band gap in this material. And now I've labeled a few features that I want to mention in a little more detail. One is that we can observe the holes, the absence of electrons. So the holes are our mental creation for the absence of electrons, and we can observe the holes in the valence band. And in this blue region here, we can observe the electrons that have been promoted into the conduction band. And then another feature, which is rather dramatic, is you see that this is kind of beating. It's like bright, dark, bright, dark, bright, dark going up. And we see some very clear oscillations in the signal. And it turns out these are coherent phonon motions, which I need to explain, in which the excitation energy of the photon eventually is delivered to the lattice, and the whole lattice starts breathing, basically. And we see that in the beating of the XUV absorption. So let's just pick this apart for a moment. So if we construct a line out of a few of these signals, like one could be very early time, like 10 to 50 femtosecond. Here's a line out of the holes. This is a good region to focus on. Here's the upper limit of the valence band, the lower limit of the conduction band, and here are the holes. And what you realize is that these holes are not thermal. We call them hot holes. They're born with excess kinetic energy. And we can follow these holes, for example, as they thermalize. I'll show a little picture in a moment. And then we see this kind of, it looks almost like a derivative feature. It's kind of a little more complicated regime, but this derivative feature is actually composed of kind of multiple effects. The whole band gap actually shifts a little bit as a result of the carriers, putting the carriers in the conduction band. It broadens to some extent, and it gives this kind of strange derivative shape, but primarily it's the electrons in the conduction band that we're able to observe. And then you can see at this longer time how these have already relaxed quite a bit, like the hot holes have nearly disappeared, and there's a shifting happening, as these carriers are relaxing and depositing their energy into the lattice. So we can do kinetics at quite an exquisite set of time scales. And this one happens to be the very earliest time, happens to be about 15 femtoseconds. But in a number of experiments in our lab, we're looking at even a few, 1 to 3 femtoseconds. And that earliest time, we attribute that to what we call carrier-carrier scattering. It's the interactions of the carriers trying to achieve a Boltzmann type distribution. And then those hot carriers will deliver their excitation to the lattice on a much longer time scale, like about 400 femtoseconds. And that's a carrier phonon scattering, where the energy of the carriers is now delivered into the lattice. So in a little cartoon-like way, we create these hot holes here, and we create these hot electrons. And the very first thing that happens is they become Boltzmann-like, but at a very hot temperature. And then they cool down and try to achieve a closer to room temperature. And in the process of cooling down, they're delivering their energy to the lattice. Now, the net result of that is that we create what we call coherent phonons. Now, a phonon, we can think of it as like a traveling wave of moving nuclei through a lattice, basically. And a way to think about it is you had an original lattice that looked perfect like this, but now you're going to have a lattice that starts oscillating, where the distance lengths are longer and shorter, and we have a compression wave kind of traveling through the material. And this happens very readily by what we call a displacive electronic mechanism, where we excite up, and we're at a totally wrong place in the band region for the lattice distances, and then they have to relax, and that will be happening on kind of a coherent way in which all the atoms start moving collectively together. There are several mechanisms that have been described for this. I'm just going to focus a little bit on the displacive one, which you can see here, for example. So we excite, and we're like way out of whack for the original spacing and now the new spacing. And so the atoms will all start oscillating together. So here are those phonon interference patterns occurring as they're collectively moving in and out. The XUV has a change in absorbance. So it recognizes that through the eyes of the tellurium, that this wave is compressing and elongating and changing the frequency of the XUV absorption. And then we see this, what looks like beating here of the coherent superposition of these phonon motions. And here you can see it much better in the line out. So if it doesn't look believable in the color map, you see it just super clearly here, how it's oscillating. And this oscillation is actually composed of two frequencies, one about 5 terahertz and one about 3.7 terahertz. And we can fit not only the frequency, but also the phases. And the phase gives us some new information about the mechanism. And what you see is that these two modes in the Fourier transform are showing us that one is a A1G mode and one is a E1G type of mode, and they can be formed by this displacive excitation. Okay, so what are those two modes in a material like molybdenum telluride? Well, the A1G mode is when we have this compressive elongating wave across the layers of the 2D layered material. And the E1G is when we have these waves of modes along the layers. And normally the E1G is very difficult to observe. It's rarely observed, but it turns out the XUV is so sensitive to these motions and the changes in absorbance that the E1G shows up very, very clearly in this case. So I hope this has maybe whet your appetite for the types of things that can be done in X-ray and XUV with very short pulses. And of course, I can't do any of this myself in a way. And so it's all these people in the group who have participated, many of whom I had the pictures on the individual slides where there were big contributors. These people are making experiments work that are extremely difficult, to train these lasers and keep them operating at the levels that we need to make these photons and to perform the experiments. And it's all tabletop work in the laboratory with attosecond and few femtosecond and longer, kind of transient absorption and reflectivity types of measurements. And I'd like to thank you for the invitation and be really happy to answer any questions.
All right, thank you very much for Professor Leone, and we have some time for questions and answers. So if you're in the Zoom chat and if you feel like asking a question, you can raise a hand and we'll be able to unmute you. Or if you are on a YouTube live stream, you're very welcome to put your question as a comment on the YouTube and we will be able to read it out here as well. So any questions from the floor? If there are no questions yet, maybe I have a question for Professor Leone. So yes, in the presentation, there are a number of two-dimensional plots with energy and time delay. So I'm just wondering how those plots are acquired experimentally. So in the case,
let's go to this. So on each time slice, you can almost see them here. For example, that's one slice and that's one slice and that's one slice. And those slices were like the tripwires of the horse traveling. So those are our time delays we set by the mirror pump probe delay. So the mirror moves to a position and that's choosing a time delay. And then the X-ray camera acquires, for example, a number of pulses, and we usually acquire with the pump on and the pump off. So we can have, the difference, the differential spectrum to see the change. And so these signals are the change, basically. So it says here like delta OD. So that would be the change in absorbance, for example, at each slice. And then you move the time delay and do it again and do it again. So this must have 50 to 100 time slices in this little part here. And each one with the pump on, the pump off. And then usually at the end of the measurement, we put in a gas and we get accurately the time zero by another measurement. So we do what would be called a cross correlation. So otherwise the time could be drifting as you're doing the measurements. You need either an interferometric stabilization or some way to get the time zero accurately. So that's usually done pretty much after each run or something, we would do that. And so now these could be acquired, like a slice could be acquired in a few minutes or something, and then you have to move it. So it's an hours, you know, it's not a whole day, but it's like hours type experiment.
Yeah, thank you very much. Would anyone else like to raise a question? Cyclone, any questions on your side? I have lots of questions. I can spend the next 10 minutes.
Don't be afraid to write something in the chat or.
Yeah.
Go ahead. Yeah.
Yeah. So So in iodine example, so you show the two-dimensional plot, and there's also a path on the right side. So I'm just wondering, what's that? What is that?
The isopropyl iodide.
Yes, isopropyl iodine example. So yes, there's also a path on the right.
Over here. Yeah. So it's subtle because there are in the XUV there are two transitions that reveal the I atom, and so you know, if I drew the full picture down below here, there's a doublet. There's a spin orbit split doublet inner shell, and so this feature here in a way corresponds over here. So you see it's not in line. This part is not in line with the atom, and so it's showing from the two different inner shell transitions what, you know, how you arrive at. So this part is from one of the inner shell transitions, and this part is from the other. This one shows it like maybe a little more clearly, but you see it over here, maybe where this number 2 is blocking. There's a ghost of information here that corresponds to what was over there. Yeah.
Yeah, that's all interesting. And any other questions, you can type in the chat. You can raise your hand. Yes, Dylan, I see.
Hello. Thank you very much for the talk. It was really interesting. I had just a quick question, I guess. Do you think you could speculate, I don't know, how much faster do you think it's possible for us to get with this?
Right.
Is there an upper limit or something?
Right. So there have been some measurements from the Ferenc Krauss group and Reinhard Kienberger down to 10 attosecond or so, and I think they're correct. You know, there are good valid measurements down to about 10 attoseconds. And if you want to go shorter, well, you have to realize that the bandwidth is enormous then, you know, so you're talking about you'd have a bandwidth of 1,000 electron volts or something like this. And I don't think anyone has really thought about yet how to take advantage of that. You know, if you could make, so people talk, there's a few papers, people talk about femtosecond pulses, which would be below 1 attosecond. And the thing is, no one has really thought much about how to employ these in real measurements because it's covering such a broad spectral range. And how do you use that in something feasible? You know, so that's where the issue is. So the measurements are all caught up in the time energy uncertainty, basically, and many arguments, of course, with theorists and many people about what's real and not real, and whether you can you really measure something to that level. And like a phase shift of light could easily mimic a real time delay, you know, that you maybe want the real time delay, but what you get instead is a phase shift of the light. So it's very, challenging right now. But I think there are good measurements down to about 10 attoseconds so far.
Okay, great. Thanks a lot.
Yeah, thanks for the question. In our lab, we've reliably measured like a little bit below 100 attosecond delays in ionization and things like this. I didn't talk about them, but we have reliable measurements down to that level with interferometric stabilization and so on.
Cool. Any other questions? If not, I'm going to throw another quick question, something that was mentioned very early in the talk. So Professor Leone, you have also mentioned that X-ray can achieve chiral sensitivity. So I'm just wondering how that's usually done, because I assume most of the spectroscopic methods are not sensitive to chiral activity.
So in several groups, they are making circularly polarized X-rays, and then that gives you access to the chirality. And if you look at especially photoelectron, where you knock an electron out of a molecule, the chiral sensitivity is really strong. So if you use right-hand circularly polarized light, you have a chiral molecule, the electron comes out in a different direction due to the chirality. And so this works very well. There are groups in France and so on that have been working on this. And if you do in materials, it's called magnetic circulardichroism. So you just switch the polarity of a magnetic field, and you see the signal changes dramatically with chiral, with the circularly polarized light. So we've done some of that in our own lab to make polarized, to look at magnetic materials, and you see this very readily.
Right. Thank you. Any other questions from the floor?
So the thing in the visible optical, just to say, the circular dichroism in the visible optical is like a really small effect. But when you look at the local single atom level, the chirality effects can be really big. And that's what people are exploiting by going into the X-ray in this way. So the X-ray, circular magnetic dichroism is like the best example of this. They're really big, huge effects.
Thanks for the answer. Anyone else? If not, I'm going to throw in my last question.
Sure.
Yes, it's a final question. So far, I think most of the experimental results presented are about the absorption spectrum, but we also know that after the excitation, the molecules will be in a very excited state, and in that case, there could potentially be a relaxation process after that. So I'm just wondering whether that relaxation process and the fluorescence from that de-excitation process will be of any experimental interest in the investigation of those phenomena.
There are quite a few examples, and I didn't show, like we have a recent paper, Nature Communications, on finding unobserved dark state in pyrazine. So we followed the whole relaxation process, and we see that there's a new state that everyone had missed essentially in the dynamics, as it's cascading down. So this is exactly what we're doing, finding new states now and so on, so that's a big area for us to try to start with molecules that we didn't understand before, and then, or there's missing information, and then we can see it, pick it up with the X-ray.
Yeah, great, thanks.
Yeah, great question.
Any other questions from the floor? Maybe we'll just wait for 1 or 2 more minutes. If there are no more questions, then maybe we can leave it here, but do ask questions. Okay.
I'm happy to stay around if anybody wants to just ask quietly after.
Yes,
also.
And if you are shy to type your questions in the chat, you can always, you can private message Prof. Leone on the chat, just to Professor Stephen Leone, then only he will see the message, not everyone else. So if you like a bit more privacy, that's what you could potentially do. Yeah. Yeah. Otherwise, if you don't have any other questions, you could leave. And then just as a bit of last minute advertisement, next week we'll have Professor Thomas Ebbison, who will be visiting us in person from France, and that will be hosted at the chemistry department. We'll send out emails later in the week, so do check that out for the talk next week. And of course, it's great to see so many of you coming today. And if you have any questions, you are very much welcome to hang around and ask the questions. Otherwise, if you have other commitments after this, or if you're running off to dinner, you could leave the meeting now, and I'll stop the live stream.
Okay, thank you very much.